All right, in this video, we're going to talk about valuing limits algebraically. Thanks to Mr. Turkington letting us use his notes. Very good notes. But so far we've learned how to evaluate limits by looking at their graphs or making tables. But one of the main issues that we run into are discontinuities. So as it reads on the top, one of the main problems with evaluating limits through direct substitution is something like this. So that means, let's say you try to evaluate the limit of f of x as x approaches c, and you plug c in and you get something weird like 0 over 0 or infinity over infinity. All right, those are called indeterminate. So they're a little different from undefined. They're similar that it's not a real number, but other than that, they're different. So like 1 over 0 is different from 0 over 0. But 1 over 0 and 2 over 0, those are considered like the same thing. Those are considered undefined. But indeterminate forms would be something like 0 over 0, which is different because normally like something divided by itself is 1. But we also know you can't divide by 0. So that's why it kind of falls in its own category. So 0 over 0, infinity over infinity, infinity times 0, infinity minus infinity. All right, can't determine what they are. So they're going to have interesting limits. So we're going to do a lot of examples that when you do direct substitution, so that means plug in the value for x, we get one of these forms. What do we do? All right, so we'll go through a bunch of different examples. And like it says, there's something slightly different about each one. All right, so for number one, let's evaluate the limit as x approaches 3 of x squared minus 4x plus 3 over x squared plus x minus 12. Let me get my calculator ready because I'm sure I'm going to need to use it eventually. All right, so if we plug in, so we do direct substitution. So we plug in this value for 3. All right, what happens? We get 3 squared. Oh, of course that didn't pop up right now. Like I deserve that. It's gonna do it again. I gotta wait. Maybe it won't. All right, minus 4 times 3 plus 3 over 3 squared plus 3 minus 12. All right, so we get 3 squared minus 12, so that's negative 3 plus 3 is 0. And then 3 squared plus 3 is 12, minus 12 is 0. All right, so we get something 0, 0 that's indeterminate. So that doesn't mean the limit doesn't exist, all right? Because we know that when you have, just because you don't get a real number, doesn't mean you're going to have a limit that doesn't exist. Limits don't exist when the left-hand limit doesn't equal the right-hand limit, but we might have a left-hand, right-hand limit here. So let's look at a graph and investigate this a little bit. So I'm going to plug this in my calculator. And direct substitution is a great way to approach limits at first by just plugging in the value for x. It doesn't always work, but it usually does work, except in math classes, right? In math classes, we try to challenge you. If we always gave you one that you just plugged in and worked for substitution, that'd be too easy. But like most functions are continuous, like all polynomials are continuous. So for most limit, when you're evaluating most limits, you could just do what we just did, but we saw an issue. So we're going to investigate it now with a graph. Right. And if we look at 3, well, it looks pretty continuous at 3. So we'll trace it and see what's going on here. So we see, all right, as you get closer to 3, it seems to be getting closer to like somewhere between like 0.25 and 0.3. So somewhere around like a third. That's what the limit seems to equal, but f of 3 is undefined. All right, so what we have here is a removable discontinuity. So that means when you have a rational function with a removable discontinuity or a hole, right? If we pull this back up here, if we were sketching this by hand, we would not do what the calculator did. We would put an open circle here to show that the function is not defined at x equals 3. And if we were graphing it without a graphing calculator, we would have to know that that existed there. And the way we would know is by factoring it and seeing that the factors cancel out. So if we factor the numerator, that would be x minus 3 times x minus 1 over x squared plus x minus 12. So that would be x plus 4 over x minus 3. So that's how algebraically we could see that this has a hole at x equals 3, because if we were to simplify this, we can cross these off, because for any value of x not equal to 3, so for all values of x where x is not equal 3, like that part that I just canceled out is going to essentially just equal 1, because it's the same number over the same number, right? If x is 10, what I just canceled out, that'd be 7 over 7, that's 1. If x is negative 100, that'd be negative 103 over negative 103. It cancels out, it's just 1. So this function here is going to be equivalent to x minus 1 over x minus 4 for all values of x except when x equals 3. And since it equals 1 for all those other values, like this won't affect the graph in any weird way, like an asymptote will. So now if we wanted to do example 1 without a calculator, we would have to factor it like we just did in green, cancel out the whole, and now find the y coordinate of the whole by plugging 3 in for x. And now we could see what the value of this function is at the whole. And we get 2/7, which is the same answer that we got when we looked at the graph. All right, if we look at, like, if we just graph like y equals 2/7, all right, we can see that it crosses the graph right where, let me get rid of this, where the function crossed 3. All right, so the first way, if you have a rational function and you try to evaluate the limit using direct substitution and you get an indeterminate form, that's a good chance that you have a hole there. So what you should do is factor it, cancel it, and then use the simplified version to see what the y value would be at that point. All right, and the reason why this hole occurs is, again, because we simplified this to x minus 1 over x plus 3. I think I typed, what was it? It was x minus 1, x minus 3, x plus 4. There you go. And notice how these two functions look exactly the same. And that's why we're able to use the black one to determine where the y coordinate of the whole would be, because all the points are the same except where x can't equal 3, because you're divided by 0 there. All right. Ooh, I hate when that happens. So example 2 is going to be very similar. Now we have a different type of factoring going on. So for example 2, we have x cubed minus 8 over x minus 2. All right, so we plug in 2 and you'd get 8 minus 8 over 2 minus 2. So 0 over 0. All right, indeterminate. Okay, so now we could take this function and factor it. So now we have a difference of 2 cubes. So that's going to factor to x minus 2 times x squared plus 2x plus 4. All right, so that's a formula that I will show you in a second over x minus 2. Now I would write the formula out. I promise I know what the formula is. I taught algebra 2 for a while, but it's really hard to write like this with the cursor and the mouse. So I'm going to pull it up. Difference of 2 cubes formula. And I just want to point out, if you ever need to memorize this formula, and this year you won't have to because it's a COVID year and we don't need to memorize things in a COVID year. I notice how sum of 2 cubes and difference of 2 cubes formulas are very similar. The only difference are the signs. So like the x, y, x squared, x, y part's the same. Now, when it's a sum of 2 cubes, it goes, this is the same sign. So same sign as whether it's a sum or a difference. All right, and then this is always the opposite sign. And then the last sign is always positive. So SOAP is a way to remember the signs. All right, sweet. So you see 2 perfect cubes being added or subtracted, you can use that formula. So now we could cancel it out. Let me erase this. Sorry, this takes way longer than it should. I apologize. All right, so cancel this out. And now we see that this function here is going to be identical to this function, except where x equals 2. You're going to have a hole because it's a hole, not a vertical asymptote, because the x minus 2 over x minus 2 is going to cancel out for all values of x except 2. And when x is 2, you get 0 over 0, which is indeterminate. But for any other value of x minus 2 over x minus 2 is going to equal 1. So you can use this as a guide to see what the function would equal at 2. So you plug in 2 now to evaluate that, and you get 2 squared plus 2 times 2 plus 4. Hey, that's pretty funny. It's 4 different ways to write 2 times 2. 2 squared, 2 times 2, and 4. So you get 4, 4, 4. You get 12. Bada bing, bada boom. That's the answer, right? And then you could also like just graph it and look and or use a table and see what's happening as you get closer to that value and confirm that, all right? But I'll spare you that for now. All right, now, example 3. We plug in 4 and we get indeterminate, right? So we're trying to do example 3 by substitution. So you plug in that, you plug in that, you get square root of 4 is 2, minus 2 is 0, 4 minus 4 is 0. All right, so now what do we do? Well, in the last 2 examples, example 1, we had a quadratic over a quadratic. So we were able to factor them, and then, you know, the x minus 3 that was causing the problem canceled it out, and that's how we got rid of it. For example 2, the x minus 2 is causing a problem, so we canceled it out. All right, here we can't really factor this. Now, technically we can, all right? You could actually factor this because we know that difference of 2 squares, like a squared minus b squared, is going to equal a minus b times a plus b. And even though x is not a perfect square, but 4 is a perfect square, you could rewrite it as like the square root of x squared, and that's equivalent to x. And then minus 2 squared, that's equivalent to 4. And then you could actually factor it by rewriting the x as a square root of x. And you would get root x minus 2 times root x plus 2. And then that would solve our issue. That would cancel out the root x minus 2s. So like that and that would cancel out. Now that's really hard to see. So I'm gonna give you another trick, but what I just explained works. It's fine if you notice that. But the thing I'm about to show you is more applicable to more situations, all right? When you have like a radical minus a number like this, all right? And this will make more sense in the next example, but try multiplying it by the conjugate pair. So it's sort of like, instead of doing what I just showed you when we did the last 2 examples, instead of factoring, going in reverse. So like multiply it by the factor that will get rid of the radical by squaring it. And conjugate pairs are just defined as like, if you have a sum of any 2 numbers, so like for any binomial, its conjugate pair is just the difference of the same 2 numbers. So like the conjugate pair that goes with root x minus 2 would be root x plus 2. All right, so if we multiply the numerator by root x plus 2 and the denominator by root x plus 2, it accomplishes a few things. All right, for one, we're multiplying by 1, so we're not changing anything. All right, root x plus 2 over root x plus 2 is 1. All right, what else it does? It gets rid of the radical, and specifically, when you multiply like these, you get root x times root x is x, and then root x times 2 is 2 root x, and then negative 2 times root x is negative 2 root x, that cancels out, and then negative 2 times positive 2 is negative 4. All right, so by multiplying by that form of 1, we now have an x minus 4 in the numerator, which will cancel out with this x minus 4 in the denominator, which was already there. And then we also have that root x plus 2 from that we haven't done anything with, but we just multiplied the numerator and denominator by root x plus 2. So that's got to stay there. But at least root x plus 2 does not equal 0 when we plug 4 in. And, you know, x minus 4 will equal 0 when we plug 4 in. But would you look at that? It cancels out. So now we just rewrote this as 1 over root x plus 2. And now we can use direct substitution with this, which is going to be equivalent to the original function for all values of x, except where x is equal to 4. But who cares? We're not evaluating f of 4. We're assuming that this is f of x. I just named it f of x. Maybe that's not its name, but that's what I'm naming it. But assuming that, right, that's f of x. Who cares that x can equal 4? We're not doing f of 4. We're finding the limit, which is different from doing f of 4. But if this function has the same graph as this function, except for the hole at x equals 4, then we can use that to evaluate the limit. So that's what we'll do. We'll plug in 4 in for x, and we get 1 over 2 plus 2 is 4. So we get 1/4. All right. So what was the issue? What was the problem? We were dividing by we were dividing by 0. So we had to get rid of that by multiplying this by its conjugate pair, and then it canceled out. All right. And I also showed you another way where you could factor this to root x minus 2 times root x plus 2. The reason why I didn't go with that way exclusively is because in this next example, example 4, you couldn't do that. But we could now get rid of this part, this root h plus 4 minus 3, because now we're going to see when we do direct substitution with that, that part's going to equal 0, and we can't divide by 0, and that's the problem. And we're going to get rid of it by multiplying by the conjugate pair. Now, which conjugate pair should I use? Should I use h plus 5 or root h plus 4 plus 3? All right. Well, it's one tool in your toolbox, and those are both things that you could try. So if you tried one way and it didn't work, you could try it the other way. I'm getting a message. Let's see what it says. Oh, no problem. So the issue is really dividing by 0. So I'm trying to get rid of the root h plus 4 minus 3, because if you plug 5 into there, you're going to get square root of 9, which is 3, minus 3 is 0. So we want to get rid of that. So I'm going to get rid of it by multiplying the denominator and the numerator by root h plus 4 plus 3. So that's what it means to be the conjugate pair. It's the same numbers, but instead of subtracting, we're adding. All right, and then root h plus 4 plus 3. Okay, so now look what happens, all right? When we multiply these out together, so we do root h plus 4 times root h plus 4. That's root h plus 4 squared. So that will stay. And then root h plus 4 times 3 is 3 root h plus 4. And then negative 3 times root h plus 4 will cancel out. And then negative 3 times positive 3 is negative 9. And would you look at that? That's going to equal h minus 5. I'm not going to rewrite this part because it takes a while to write that stuff. But now if we take this and we multiply across, we're not going to FOIL, because we want to keep it factored, because we now have an h minus 5 in the denominator. And if we were to plug in 5, we would be dividing by 0. So that's no good. So we rewrite it. So we keep it factored as h minus 5 times root h plus 4 plus 3. All right. And then now these will just cancel out. Bang, bang. And now we see that this is equivalent to this as long as h does not equal 5. And the reason why that's true is the reason why I could confidently say that those two graphs, right, this one right here, this original function and this function, the reason why I could say that they're equivalent is because I didn't do anything other than multiply by 1. I multiplied by this number that is a form of 1, as long as h doesn't equal 5. And I said that h couldn't equal 5. So to finally evaluate this limit, I'm going to erase all this stuff now so we have room and see what we're doing. All right, so to evaluate that limit, oh, I lost my fraction bar. That's embarrassing. Oh, I don't even need it anymore. Oh. So to evaluate that limit, where's my marker? I'm just going to use this function, which is the same graph, except at h equals 5, we're going to have a hole. So we plug in 5, and we get square root of 9, which is 3, plus 3. and we get 6. Right? And that's our answer. And just to further reiterate that the green thing I have written and the original function are the same graph, just to prove that to you, is we'll write it out and we'll graph it. So if I were to do h minus 5 over the square root of h plus 4 minus 3, I'm writing h, so it's not going to work. You have to use x. All right, and then if I do square root of x plus 4 plus 3, see, it's the same exact graph. The only difference is if I trace it. So I go 5. Right, for the blue one, it's undefined, because if you plug 5 into the blue one, which was the original function, you'd be dividing by 0. But if we plug it into the red one, you would get 6, which is exactly where the hole would be. So by multiplying the numerator and denominator by root h plus 4 plus 3 over root h plus 4 plus 3, we were just multiplying by a form of 1, where a couldn't be 5, to rewrite that. And we use that to see like what the function should equal at that value, which is exactly what a limit is. All right. All right. A few more on the next page, not as many. All right, so here, example 5, what's causing the problem and how do we get rid of it? So, so let's take this function here. Let's try to solve it by direct substitution. Plug in 1, plug in 1. Oh boy, we have an issue. We would get 0 over 0 minus 2 over 0. So what we could do is multiply the numerator and denominator by x plus 1, so that, we'll try to condense this down to one fraction and see if that helps anything. All right, so we get the limit as x approaches 1 of x plus 1 minus 2 over x squared minus 1, because now I'm just adding the numerators together because the denominators are the same. X minus 1 times x plus 1 and is the same thing as x squared minus 1. And when you add two fractions, you add the numerators and keep the same denominators. Now, by getting a common denominator, and we condense this down to one fraction, we're now able to simplify it. Now, this may not always happen, but it does here. So x plus 1 minus 2 is x minus 1, and then x squared minus 1 is x minus 1 times x plus 1. And so by factoring it, we see, oh, there's a hole at x minus 1. Well, that's equivalent to this original function, so there's also a hole at x minus 1 there. So this original function is equal to 1 over x plus 1, except x can't equal negative 1. Oh, sorry, x can't equal 1 because of the hole we just canceled out. But for every other y value, like this will have the same y value as this. So we can use that as a guide and plug 1 in there and see what we get. And we get 1/2. So basically, by doing all this, we see that this function here has a hole at 1, 1/2. So that means that the limit as x approaches 1 is going to be 1/2, because by knowing there's a hole there at 1, 1/2, we know that as there's like this open circle here, but hole means it's going to be like continuous, like left continuous and right continuous, like right at that point. It's just at that one point, I guess I said that wrong. It's really not left continuous or right continuous because we don't know this point. But by knowing there's a hole there, you know that as you approach 1 from the left, it'll get closer to 1/2. As you approach 1 from the right, y will get closer to 1/2. So just in general, with these 5 examples, you're basically looking for holes, and holes occur when you have the same factor in the numerator and the denominator. And once you cancel them out, then you can use that simplified version to figure out what the y value should be. And that's what a limit is. All right, example 6. What was different about this problem? All right, well, in this problem, we just talked a lot about holes. All right, in this problem, if we plug in 2, we don't get 0 over 0. We get 4 minus 2 plus 3. So 4 minus 2, 4 minus 2 is 2 plus 5. Wow, my bad. So 4 minus 2 is 2 plus 5 is 7 over 0. All right, so now we don't have 0 over 0. We have 7 over 0, which is different. All right, that's undefined, which tells me that there isn't a hole. There's probably going to be some sort of asymptote, though. All right, and if we were to factor this, all right, x squared minus x plus 5, that can't be factored, but it could have solution. So who cares what it factors to? Like, well, it's not going to factor with like rational numbers, but it could have 2 solutions that you could find using the quadratic formula. But if it doesn't factor with rational numbers, then you know that x minus 2 is not a factor. So nothing's going to cancel out now. So since x minus 2 is a factor of only the denominator, that means there's going to be a vertical asymptote at x equals 2. So if we were to sketch this graph, as we approach 2 from one side, you know, it may approach infinity. From the other side, it may approach negative infinity. So since it approaches different values from either side, and it doesn't approach a specific value from either side, right? When there's a vertical asymptote, if it's asking for the 2-sided limit, you could just say the limit doesn't exist because there's no specific number that y is approaching as x approaches 2 because of the vertical asymptote. And you can get that without looking at the graph by just knowing that x minus 2 is only a factor in the denominator. So therefore, there won't be a hole. There will be a vertical asymptote. And if you want to just confirm that with a graph, which you should always do with these, you have a graphing calculator, like use it. There's a lot you can do, even if it's not like using the CAS capabilities, like the stuff that does all the work for you. I'm sure there's a way you could do limits on this calculator too, now that I think about it. I just haven't been teaching calculus long enough to know that off the top of my head. But I'm sure if you want to explore that one day, bring it up in class and we can find it. But nonetheless, just the basic graphing capabilities show you that there's a vertical asymptote at x equals 2. All right, zoom out. Zoom out. So therefore, the limit does not exist for example 6, because on the left, it's approaching negative infinity, approaching 2 from the right, the limit's approaching infinity. All right. All right, these last 2 examples, let's just do them together. So same strategies that we used just before. So example 7, we plug in 0 and we get 0 over 0, which tells me there's some sort of hole. So to get rid of it or to find it, or rewrite this without the x in the denominator so that we don't have to divide by 0, we're going to multiply this numerator by its conjugate pair. So that would be root x plus 2 plus root 2. But you also have to do that to the denominator. All right, so if you have so basically, when do you do this? So when you have a factor in your denominator that's causing you to get 0 over 0, you want to find the binomial that has radicals in it and multiply it by its conjugate pair, like we just did here. So now the numerator, this is like a minus b times a plus b. It's going to be a squared minus b squared. So x plus 2 minus 2 over x times root x plus 2 plus root 2. All right, and then look what happens. We found the hole by rewriting it this way, because these 2's will cancel out, these x's will cancel out. So we get 1 over root x plus 2 plus root 2. So to figure out what the limit is as x approaches 0, we can use this version here. You know, x can't be 0, but again, we're not doing f of 0. We're doing the limit as x approaches 0. And we see that there's a hole because this canceled out. So we can use this as a guide, plug in 0, and we get 1 over root 2 plus root 2. So that's 1 over 2 root 2, which let's rationalize that because, you know, basically in calc honors now, so we want to do this the right way. So we get root 2 over 4, and there it is. All right, and root 2 over 4, it's like 0.7 over 4. So I don't know, it's like around like 2, forget I said that, that's not right, but 0.2, but yeah. So again, you confirm that with a graph. So like if you wanted to double check this, you could, we got root 2 over 4. So if we did square root of x plus 2 minus root 2, that whole thing divided by x. All right, and we look at what's happening around 0. So I'm going to zoom in a little bit. Nope, I did not do that. Zoom box. All right, and we could see, if we were just to see like what the y value is for root x plus 2, root 2 over 4. Sorry, I'm bad at like multitasking and talking and stuff at the same time. But yeah, we could see like, although it's undefined at 0, which we'll see by tracing it, you know, that's what the y value would be at 0 if it was defined. See, undefined, but should be around 0.354, which is root 2 over 4. All right, okay. Last one, then I'll let you work. And like I said, I'll shorten the assignment a little bit because it went longer than I thought, which I always do. So x minus 1 over root x minus 1. All right, so what should we multiply by? Well, you can, you know, x minus 1 is a conjugate pair of x plus 1. But if we did that, it wouldn't be getting rid of the issue. If we multiplied the numerator and the denominator by x plus 1, then like we would, that wouldn't get rid of this, which is equal to 0 when you plug 1 in. So since we're trying to get rid of that so that we could plug in 1 and not divide by 0, we're going to multiply the numerator and denominator by root x plus 1. And now when you multiply these together, root x times root x is x. See, this is the root's only under the radical there. That's kind of confusing. There you go. When you do root x times root x, you get x, and then root x minus 1 is negative root x. 1 times root x is positive root x. Negative 1 times positive 1 is negative 1. And then in the numerator, you get x minus 1 times root x plus 1. All right, so that'll cancel, that'll cancel. All right, so now we see, okay, this function is equivalent to this function for all values of y except, or for all values of x, except when x equals 1. But since, you know, x equals 1 got, x minus 1 got canceled out here, that means there's a hole at x equals 1. So you plug in 1 and you get 2. And so that would be what that equals. The limit as x approaches 1 of x minus 1 over root x minus 1 would be 2. All right. So if you have any questions, let me know. I'll go over anything you want from now until 3:15. So for homework, I'm just going to change it to the odds. So like half the time I thought you would have left. I have a little more, but you have about 20 minutes left. So just do pages 21 and 22, just the odds, and 1 through 11, the odds. And the answers for pages 21 and 22 are here. So as you work, check your answers. And if you get something different, just ask. All right. And then for this, I want you to start from 1 and just do 1 through 11, but you can do every other one. So you're not doing too much extra work. I just want you to work in class. And then if you don't finish, then have just a little bit for homework to do. All right. So if you have questions, hang back and ask them. If you don't, you can leave. But if you have a question later on, just hop back on the Zoom and happy to help you. Thank you. See you.